All right, sorry about that. Okay, so at long last, who wants to ask the first question? Well, I guess we're done then. Okay, thank you all for coming. Yes?
Can we do some examples with p squared equals a cubed?
Some examples with p squared equals a cubed. Okay. Let's make something up here. Okay, so suppose we had a planet that has, how far you want it to be from the sun? Pick something. Far, okay, all right. Let's make a planet that is 10 AU from the sun. How's that sound, okay? So, it's about right for Saturn. So Saturn is 10 AU from our buddy, the sun. What is its orbital period? So, we know that p squared is equal to a cubed, where p is in, what do we measure p in to make this work? Years, Earth years, right? And a is measured in AU. So Saturn's 10 AU from the sun, so that means I say what? P squared equals 10 cubed. So for Saturn here, p squared is equal to 10 cubed. What's 10 cubed? 1,000, right? 10 times 10 times 10 is 1,000. 10 to the third power means 1. 3 zeros after it. 10 times 10 times 10. So p squared is equal to 1,000. So what's p? And I don't literally mean what's the number. I mean, you know, I'm not expecting you to do that in your head right off here. But in other words, how do I find p? What do I do? I square root, right? Square root undoes the square, so to speak. So p squared is 1,000. Then p is the thing which, when you square it, gives 1,000. Well, the square root of 1,000, when you square it, would be 1,000. So p is the square root of 1,000. What's the square root of 1,000? I don't know, 30 something. So you whip out your calculator, and on my computer here, I can say SQRT 1000 in the Google search bar, and pops 31.6. So this would say that a planet with at about, and this is about right for Saturn, if it were exactly 10 AU from the sun for its semi-major axis, then its orbital period would be 31.6 years. Yes?
Are you going to let us know how many sig figs you want for the math answer?
I'm not going to be particularly worried about it. Now, you know, don't say 30, don't say 31. Just put 1 or 2 places after the decimal point will be good. Yeah. Yes?
There was this one question in homework, and I don't know, maybe it's related to this, but I didn't know how to calculate it. It was like a planet with the same mass as Earth orbiting at a distance of 1 AU from a star with 36 times the sun's mass.
Yeah, we'll do that in just a second.
Alright.
Yep, okay. What did you do? Yep.
Will we get a formula sheet?
Yeah, there's going to be a formula sheet. Yeah, there will be a formula sheet. Yep. And you don't have to memorize like the gravitation constant. I mean, everybody knows it's 6.6 times 10 to the minus 11. 6.67 times 10 to the minus 11. But you've known that since kindergarten, but I'll still give it to you. So, okay. So this would be if I was told what A is, figure out what P is. What if I had to go the other way around? So for example, can I erase this? Okay. So what if I have to go the other way around? What if I said, Zorkon orbits a star with the same mass as the sun. My wife alleges that Zorkon is the name of my home world, so that's why we have Zorkon. Zorkon orbits a star with the same mass as the sun. with a period of, let's say, 5 years. What is A for Zorkon? So the fact that it orbits a star with the same mass as the sun, do we get to use p squared equals a cubed?
Yes.
We do, because it's got the same mass as the sun. So again, we get to say p squared is equal to a cubed. So this time I know the period is 5 years. So what do I get to plug in, p or a? P. So now I have that 5 squared is equal to a cubed. Quick, what's 5 squared? 25. 5 times 5 is 25. 25 is a cubed. So how do I undo that? What do I do to find out what a is? Yeah, you take the cube root. Some calculators have a cube root button, and then you're in luck. You would just hit the cube root button. Some calculators don't, but does anybody know how can you also take a cube root by raising to a power? Taking the cube root is the same thing as raising to what power?
1/3.
The 1/3 power, yeah. So I can say that a is the cube root of 25, and if your calculator has a button that says cube root on it like that, just push that button. That's also the same thing as 25 to the 1/3 power. And typically the way you get a calculator to do that, if it doesn't have a cube root button, is you would enter 25, and then there will be a key that typically says something like y to the x. That means raised to a power. And then you could put in 0.33333333 if you like, because that's what 1/3 is. Or you could put in, if it's got parentheses, like 1/3. Don't, though, just say y to the x 1 divide 3 without parentheses, because that would raise 25 to the first power and divide it by 3, which is not the same thing as taking the cube root. So you might just say y to the x, and then you probably know 1/3 is 0.333333, so just put 25 y to the x 0.333333 4, 5, 6 times, and you'll be good to go. And then you hit the equals button, and it'll tell you what it is. I have the convenience of my Google calculator search bar here, so I'll just go 25 to the power of area code 16. How the hell did I do that? What? I don't even want to know. I'll just watch the video later. 25 to the power of, well, they give you all these things people want to do, huh? Easy. East First, 25 East First Avenue, Columbus, Ohio. Okay, who knows? Anyway, 25 to the 1/3. Why, that's 2.92. 2.92 what? What are the units? Yeah, AU. So a planet 2.92 AU from the sun would have an orbital period of 5 years, is what that would be saying. Or Zorkon orbiting a star the same mass as the sun. So remember that you can bring a calculator. I don't want you to use your phone as your calculator for obvious reasons, because your phone has internet access and you can Google answers. Not cool. So you can't use your phone as your calculator, but you can bring a calculator or rent one from me for $1, and it goes to Perkins Observatory to help them out, basically. So, but don't rent the calculator at the beginning. Decide if you need the calculator before you rent the calculator. You may decide, I can do this in my head. I don't need a calculator for this. Or I have no idea how to even do this, so why bother renting a calculator? Which I hope is not what happens. Okay, any questions about this? Okay, so what if I'm doing a homework problem and it says, and that particular homework problem from the Mastering Astronomy was randomized. In other words, it gave everybody different numbers. So to mean that everybody ought to be doing their own work, basically. I don't want it to be where, hey everybody, the answer is 6, and everybody just puts 6 without doing any calculations. Okay, so let's just go with the numbers you were given. What's the mass of that star?
36 times the sun's mass.
36 times the sun's mass, and it's orbiting how far away?
1 AU.
1 AU, okay? So, let's see, this time our planet will be, no cross. See what I did there? Zorkon backwards. It's not even funny, Claire. I made Zorkon backwards. No cross orbits a star with 36, was it? 36 times? 36 times the sun's mass at a distance of 1 AU. And then what's its orbital period? What's its orbital period? So, I'll tell you how to do this easier than the way the book would have you do it. The book has you use Newton's version of Kepler's third law, which involves g and 4 pi squared, and putting the mass in kilograms and so forth. But there's much more convenient units than that, which is what astronomers would actually use here. So, what you can use is the fact that p squared is equal to a cubed divided by the mass of the star, where the mass of the star is in terms of the sun's mass. So p again is in Earth years, a is in AU, m is in what we call solar masses. So, go back to our solar system, just to see that it's consistent here. What is the sun's mass in terms of solar masses? 1. So in our solar system, it's just p squared equals a cubed divided by 1. P squared equals a cubed. But if it's going around a star other than the sun, we can still use Earth as the standard, but we just have to divide by the star's mass in terms of the sun's mass. Now, it doesn't mean that Earth and the sun are somehow special in the universe. The people on Nocroz, the Nocrozians, could use their star as the unit of measure. They could use their year as the unit for P. They could use their A as what they could define as Nocrozian units or something like that. It would work no matter what star and planet you used as the standard. Let's use Earth and the sun as the standard. So p squared is a cubed divided by m. So in this case, we're trying to figure out what p is. So in this case, p squared is, what do I put in for a? 1. Yeah, I put in 1 cubed because we're given that it's a distance of 1 AU. What do I put in as m? 36, because it's 36 times the sun's mass. Okay, what's 1 cubed? 1. So p squared is 1 over 36. What's p? Well, I know it's the square root of 1 over 36, all that business, but in other words, p squared is 136, so you're being asked, what times itself would give 136? You don't even need a calculator. What times what? What times itself would give 1 over 36? 1 over 6. So you don't even need a calculator for that. P, you could use a calculator, but you don't gotta if you could just realize, well, 1/6 times 1/6 would be 136, so that's what I need. So P is 1/6 of a what? Year. P is 1/6 of a year. Now the question in Mastering Astronomy wanted the period in months. So if it's 1/6 of a year, how many months is that? 2 months, right? Because there's 12 months in the year, so 1/6 of 12 months would be 2 months, would be if you were asked to do that in months. So in other words, it's really not any harder than p squared equals a cubed, except for you just got to put in m, which won't be 1 in that case. If we're going around the sun, what would its period have been? 1. Which makes sense because you'd be having a planet that was going around a star with the same mass as the sun at a distance of 1 AU. In other words, it might as well be Earth. in that case, which certainly has a period of 1 year. Okay, any questions? I'm gonna double check that my phone is still happily recording. Why, yes, it is. Oh, I'm so proud. So if somebody notices that their little red thing stops blinking or whatever, let me know, because you know there's only so big a file can be. I think it'll automatically keep going after like 38 minutes, but you know once it gets to be like a certain length of the video, but whatever. Anyway, okay. So if there's no questions about that, we can move on to something else. Yes.
So how many questions is multiple choice and how many is like short answer?
There are, if my memory serves, I made it 40 multiple choice and like I think it's 10 short answer / calculation problems / mastering astronomy, you know, based on mastering astronomy or lecture tutorials or whatever. So, yeah. Yes.
Can we go over Kepler's laws again?
Kepler's laws, yeah. So Kepler's got 3 laws, and what's Kepler's first law say? The orbit of a planet is an ellipse with the sun at one focus. Yeah. So that's Kepler's first law. Yeah, that's my wife is all blessed. Did I accidentally delete that slide? Kepler's second law. Where's the first law?
Just have it.
What did I do?
It's right under the picture.
Did I do it? Oh, hi. Okay. I can't read my own slides when they're tiny. Okay. Yeah. Yeah, my wife at first when I'm coughing, I tell you guys, when I'm first coughing, my wife is all like, oh honey, oh blah, 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 and it pretty quickly turns into shut up. But I'm not coughing right now, it's pretty good, but she's coughing, because I gave her what I had, you know, because I'm such a good husband, I was generous enough to share. Anyway, I can't stop thanking you, kicking me. Kepler's first law, the orbit of a planet is an ellipse with the sun at one focus of the ellipse. What's at the other focus? Nothing, right? Okay, that's number 1. What's the second law? Equal areas in equal times, yeah. The line from the planet to the sun sweeps out equal areas in equal amounts of time. And I always emphasize that you gotta say the whole thing. It's not the line joining a planet and the sun always sweeps out equal areas. Or the time is always equal. That would make no sense whatsoever. If between 2 points in the orbit, the area was 3 times as big as between 2 other points in the orbit, how do the times compare? So in other words, suppose I had an orbit like something like this, racy, racy, race. Okay, there's some orbit, and I said, okay, there's point A, there's point B, here's point C, here's point D, and suppose I just told you, I don't know if it's true or not, probably not, but whatever, suppose that was just a given. This area from A to B is 3 times bigger than this area swept out between C and D. How would the time for the planet to go from A to B compare to the time for the planet to go from C to D? Would they be the same? First question. Crickets. Of course, I'm hearing crickets, but sometimes it's because people think they know the answer, but they're scared to death they could be wrong. that area, I'm just take it as a given. That area is 3 times bigger than this area. So is the time to go from A to B the same as the time to go from C to D? No, it is not, because it's not equal time. It's equal areas and equal times. Are those areas equal? So the times are not equal. So if the area is 3 times bigger, how do the times compare? 3 times. It takes 3 times as long for the planet to go from A to B as it does from C to D if the area is 3 times bigger from A to B as it is from C to D. So equal areas and equal times, and if the areas are bigger, the time is bigger by the same amount that the area is. That's Kepler's law number 2. Any questions so far? What's the third law?
P squared.
Yeah, I think you said P squared equals A cubed, right? Also known as the, I'll be disappointed if you don't remember. Yes, the harmonic law. Yes. The harmonic law. Yes, Kepler's third law. I feel like I gotta edit this and add harmonic law to it right now. Yeah, the harmonic law. P squared is equal to A cubed. In general, it's P squared equals something times A cubed depending on what units you use. But if you use the right units, if you base it on one planet's period and one planet's astronomical unit, so to speak, then you'll get P squared equals A cubed as long as you express everything in terms of that planet's orbital period and that planet's orbital distance. Why not pick Earth? It's our favorite planet. It's a lovely place. I mean, we're working on trashing it, but still pretty lovely, so let's pick Earth. So P squared is equal to A cubed, where P is Earth's orbital period, the year. A is Earth's semi-major axis, the astronomical unit. Any questions? Yes?
So what are we doing again?
What's that?
What are we doing again?
What we were doing just now?
We do something?
No, I
I
don't
thought
know.
you just asked us a question.
What's that?
No bad.
Oh, okay, yeah. No, I'm just saying, any more questions about Kepler's law? Kepler's law, that's all. Hey, I can beat you on that. I was at a big meeting of the American Astronomical Society. At a big, what's called a plenary talk. Everybody's supposed to be there. So there's like probably 2,000 people in the room. And I was getting kind of sleepy, so I go, yes! You had a question? I'm like, no, I was just yawning, carry on. So, all right. What should we talk about next? Newton's laws. Sure, why not? How many Newton's laws are there? 3. It's like these things come in 3s, right? So, let's see. Yeah, this is next chapter. So, Newton's laws. Newton's first law is the one that says that things move in a straight line at a constant speed unless a net force acts on them. So the way your book puts it is that, I think it says it moves at constant velocity unless there's a force on it. Well, constant velocity would mean, since velocity involves both speed and direction, if the velocity is constant, the speed and direction are constant, that's a straight line at constant speed. It's saying exactly the same thing. So an object at rest remains at rest, and an object in motion remains in motion in a straight line at constant speed, unless the forces applied to it by other objects do not add up to 0. We call the total force applied to it by other objects, when you add it up, we call that the net force on it. So a short way to say that is, unless the net force on it is not equal to 0. So kind of, the natural state of motion is just moving in a straight line at constant speed. It takes a force to disturb that and make the state of motion change. So why don't we typically observe that? Like here, I'm going to move this meter stick here. Pretty much moved in a straight line. Why did it move at constant speed?
There's friction.
Friction, yeah, friction. Friction is what made it take so long for people to figure this out, because friction is all over the place in the world. And so it's hard to get a situation on Earth where something doesn't have a net force on it. That's difficult to do. So it was hard to notice that things with no net force on them would just move in a straight line at constant speed. These days, one of the best ways to do that, at least in between collisions with the walls, is use an air hockey table. That's almost frictionless. Or if you send a puck down the ice in hockey, as it's going down the ice, it moves very close to a straight line at constant speed because there's not much friction with the ice. Okay? What's the second law say? Yeah?
Force equals mass times acceleration.
Yep, force equals mass times acceleration, or I like to say acceleration equals force over mass. The reason I like to put it that way, I don't disagree with you, but I like to put it this way because it emphasizes cause and effect, that force causes acceleration, is what it comes down to. Notice, by the way, that Newton kind of cheated, because he got two laws for the price of one. So if the total force, if the net force was equal to 0 in Newton's second law, what would that say about the acceleration? It would be equal to 0. So Newton's second law already implies that if the force is 0, the total force is 0, the acceleration is 0. How does something move if its acceleration is 0, if it's not accelerating? Is its speed changing? Is its speed and, can its speed and direction, either one of them, change if it is not accelerating? No. If it's not accelerating, that is motion in a straight line at constant speed, right? Because remember, any change in direction or speed is acceleration. So Newton's second law says if there's no total force on it, the acceleration is 0, which means it moves in a straight line at constant speed, which is Newton's first law. So Newton's first law is really just the F total equals 0 special case of Newton's second law. So he kind of got two laws for the price of one. He really only formulated two laws, but he called it three because he thought it was important to emphasize that if you don't put a force on something, it'll just keep moving in a straight line at constant speed, since that wasn't obvious to people at the time. How about the third law? What's that one? Yes?
An object, wait, no, it's not an object. I'm blanking on it.
Okay.
The force, yeah, for every force is an opposite reaction force.
Yeah, for every force, there's an equal and opposite reaction force. We have to be careful, though, because we have to realize that those forces are things that two bodies exert on one another. There are always forces on different things. Forces always come in pairs. If object A exerts a force on object B, then object B also exerts a force on object A, and it's equal and opposite. It's the same size, but pointing in the other direction. That's the third one. Which, that's what it comes down to. But it's always important to realize that there's two objects involved. If there are forces on the same object, even if they're equal and opposite, they are not a Newton's third law action and reaction force pair. And the example I gave of that when I was standing on the table, and I tricked everyone by saying, okay, what are the forces on me? Gravity down, and the table pushing up on me. Those are equal and opposite, but they're both forces on me, so they were not reaction forces to one another. The reaction force to, I don't want to get on the table. I'm standing on the ground here. The ground is pushing up on me. What's the reaction force to that? Me pushing down on the ground. They're both contact forces. What's the reaction force to Earth's gravity pulling down on me? So gravity always pulls. Newton's third law, pairs of forces are always the same kind of force. So Earth's gravity pulls down on me. My gravity pulls up on Earth. How do those forces compare? Equal and opposite. I'm pulling up on Earth just as hard as Earth is pulling down on me. But if I jump off the table, how come you notice my motion a lot more than Earth's motion? Well, but fundamentally, what's the difference? For these purposes, how come my motion is a lot greater than Earth's motion? What's the big difference between me and Earth? Mass, yeah. Earth's mass, 6 trillion kilograms. My mass, not 6 trillion kilograms. At least I hope not. If my mass was 6 trillion kilograms, you'd all be dead. So would I. Anyway. Okay, any questions? Yeah.
What does it mean to say that velocity, acceleration, force are vectors?
Are vectors, right. So your book doesn't use the word vector because I think it doesn't want to scare you or something like that. So what's a vector? A vector is a quantity that has both size and direction. Yeah, to say something is a vector just means not only does it have bigness, size, and I don't literally mean necessarily like length, in other words, just how big it is, like for example, for velocity. What do we call the size for velocity? In your car, if you're driving down the road at a certain velocity, you have to say both what along with what direction you're driving. Speed. Speed is the size, the magnitude of velocity. So the difference between speed and velocity, if you want to do it right and use the terms the way physicists are supposed to, although even physicists get sloppy when they're speaking casually, is that velocity is a vector because it involves both speed and direction of motion. Speed is not a vector because it doesn't say anything about direction of motion. So two cars going in opposite directions would, if they both are going 55 miles an hour, they'd have the same speed but not the same velocity because velocity includes direction as well. Acceleration is rate of change of velocity, and since velocity is a vector, that means you could be changing the speed and or the direction. So if something is changing its speed and or the direction it's moving, it is accelerating and it requires a force to make that happen. Questions about that? Okay, what's next? Yes?
Can you do something with like conversions? I don't know what good example.
Like doing conversions between like units, that kind of thing, like, because that's what we're talking about, is like converting units to one another. Yeah, so if you took chemistry in high school, I'm sure you did something similar to this, or if you took physics, the book talks about this, so you can read about this sort of thing in the book too. But, you know, for example, just to use something kind of out of the blue, so okay, well, yeah, the book does this example, so this is good. How many seconds are in 1 year? How many seconds are in 1 year? Now, you might be able to intuit how to do that, but the good thing about the way I'm going to show you is it keeps you from multiplying when you should have divided or dividing when you should have multiplied. A common mistake is when you're doing a conversion, dividing when you should have multiplied, or vice versa. And the way we do this is we say, okay, we start with 1 year. So let's convert the year first into days. How many days in a year? 365, and it's actually 365.24 is closer to being right. So we'll actually use that. So what I do is I multiply by 1, which doesn't change anything, but the way I write that 1 is 365, I'll just call it 25, it's about 365 and a quarter, 365.25 days in 1 year. I don't divide by 365.25 days, I multiply by it. And the way I can be sure that that's the way I have to go is I don't want the year units to be left over when I'm done, so I put the years in the denominator so that those year units cancel those year units over there. So if we stopped here, we would say 1 year is the same as 365.25 days. But we want how many seconds are in a year. So I want to multiply again. What should we convert to next? Let's say hours, okay? What do I multiply to turn this now from days into hours? What needs to go on the bottom? Is it days or hours should go on the bottom? Days, because I need to cancel that. So I'll say what? So what's the conversion from hours to days? Yeah, 24 hours in a day. So I'd say times 24 hours in 1 day. So now the days cancel one another. So if I multiply 24 times 365.25, I know how many hours are in a year. But wait, I want how many seconds are in a year. So what should I multiply by next? So if I want to go into minutes, let's say, then do I put hours on the top or the bottom? On the bottom, because I need to cancel those hours. So I'm going to have minutes on the top because I want those to live through this step. Hours have to go away. And what am I going to do? What over what? 60 minutes in 1 hour. So 60 times 24 times 365.25 is how many hours, how many minutes are in a year. One more step, and I'm going to multiply by. Yeah, 60 seconds in 1 minute. Now the minutes cancel. And so the number of seconds in a year is 365.25 times 24 times 60 times 60. And this is a systematic way to do that conversion. If you had anything on the bottom, you divide by all the things that are on the bottom. In this case, it's a bunch of ones, so that's not necessary. But if you had stuff on the bottom, you would want to divide by the numbers that are on the bottom. You could have a series of this times this times this divided by that times that, for example, depending on how you're doing how you're doing that conversion. Yes.
So will we have a chart that has like everything that goes?
So first of all, I do expect you to remember the metric prefixes, right? So in other words, I do want you to know that a kilometer is how many meters, for example? 1,000. A millimeter, how's that work? A millimeter is what in terms of a meter? So 1 millimeter, 1 millimeter is what? Not 0, 0, 0, 1. How many millimeters are in a meter?
1,000.
Yes, 1,000. If nobody said that, I was going to write email to every one of your teachers and say, what have you been doing with my students? Were you just, no, okay, so 1,000 millimeters in a meter. So put another way is 1 millimeter is 1/1000th of a meter. So you could say it's, if I want 1,000th, what do I write? 0.001 meters. What if I want that as a power of 10? That's 10 to what power? 10 to the -3rd, yeah, 10 to the -3 power, because you count how many places you had to go after the decimal point. 1, 2, 3, so it's 10 to the -3 meters. So know the metric prefixes. Know that a centimeter is 100th of a meter. A millimeter is 1,000th